And we're live. Welcome to this keynote by Professor Julian Higgins. I will let him introduce himself and his presentation. Take it away.
Thank you very much, Ryan, and thank you so much for the invitation to talk to you today. As you can see, I'm Julian Higgins. I'm Professor of Evidence Synthesis at the University of Bristol in the southwest of England. My title is Misunderstanding and Misuses of Commonly Cited Methods for Meta-analysis. It may seem a little bit self-indulgent maybe at times, but I hope you'll see that there's what I think is an important message underlying what I've got to say. So, as you will know, systematic reviews and meta-analyses have become really absolutely critical for decision-making in health and, of course, in many other areas. They're hugely influential. They inform clinical guidelines, policy-making, decision-making at government and many other organizations. And you can see in many or most hierarchies of evidence, they tend to appear at the top. This means they have become very highly cited things, not only the systematic reviews themselves, but particularly the methods for undertaking reviews and meta-analyses. And I'm often getting emails like this one telling me that I've been highly cited in the last year. This is a particularly interesting one. It comes from SciLit, which I didn't know about before, but it's a nice big database of 174 million publications that uniquely, as far as I can tell, allows you to rank everything in terms of how many times it's been cited. And here's the ranking of 119 million journal articles. And you can see that the most cited ever is a 1951 paper about protein measurement. I thought I'd look through this list and then see how meta-analysis methods are faring. And I've picked out the papers that come at the top. I've also put in a couple of R-related papers, given the nature of the conference. You see LME4 comes ahead of any of the meta-analysis papers. But among all the papers about meta-analyses and systematic reviews, we've got a gaggle of them in the 40s. I've got one in 93rd place and one in 109th place. And, I think the highest R-related meta-analysis paper is Wolfgang's Meta-4 paper, which is doing very healthily at 500 somethings. But I mean, you can see that the numbers of citations of some of these papers are really quite large. And I thought, well, and there's also the papers that when I see them cited, I usually get frustrated or exasperated that people are not really using them in the way I think they were intended to be used. So I thought I'd build a bit of a talk around the idea that these highly cited papers are often misused. And I suspect that most of what I say is not news to anybody. The challenge, of course, is what we do about it. I thought I'd take those papers and just regroup them to organize my talk. Two of those papers are about the PRISMA statement. So I'll start talking about misuse of reporting guidelines. Two of the papers are about measuring inconsistency in the domain of heterogeneity in meta-analysis. So I'll talk about the misuse of the I-squared statistic. There's, of course, Simonian and Laird's classic meta-analysis paper introducing the random effects method. So I'll talk about misuse of random effects meta-analysis. And then there's the Egger test for funnel plot asymmetry. So I'll talk a bit about how that is widely misused. Let's jump straight into the first paper is the PRISMA statement. PRISMA, of course, replaced the quorum statement, quality of reporting of meta-analyses. The initial PRISMA version was published in 2009, and of course it was updated a few years ago in the PRISMA 2020 statement. What's the paper about? Well, it's a checklist and a flowchart for how one should report a systematic review or a meta-analysis. I was lucky enough to be involved in the initial PRISMA meeting. You can see the blurry picture of the people who were attended there. And here's an example of what the work is involved into in terms of the PRISMA 2020 statement. Here are the first 15 items of about twice as many, telling you what should be reported from a systematic review or meta-analysis. And it has a template for a diagram, often called a PRISMA flowchart, a PRISMA diagram, describing the flow of studies from identification through the search through to inclusion in the review. But what's the problem here? Well, I thought I might illustrate the problem by through examples. And I thought I will just pick what's a reasonably random paper of current use. Well, I just put the most recent citation from that SILET database that had cited a paper citing the PRISMA paper. And this is what it was. It wasn't a full systematic review, but you can see how they've used PRISMA is the beginning of the materials and methods section. They say the PRISMA guidelines were used to guarantee the validity and strength of the research outcomes. This is not at all what PRISMA is able to do. PRISMA is a reporting guideline, of course. And I'm sure, I hope, many of you will recognize this problem that almost whenever we read a randomly selected systematic review, it says we did the review according to the PRISMA guideline, which is just nonsense. I mean, if we look at what the guideline is, I mean, it's about specify the methods used to decide whether a study met the inclusion criteria, how many were involved and so on. So, I mean, I could be perfectly compliant with that outcome in PRISMA by saying, well, one person decided on the roll of a die whether to include a study. And as long as it was fully reported how badly it was done, then it would be perfectly compliant with PRISMA. So as I hope we all know, PRISMA is a guideline for reporting. It's not a guideline for doing systematic reviews. And indeed, if people read these papers, they will see very clearly that PRISMA 2020 is not intended to guide systematic reviews conduct. And it shouldn't either be used to evaluate the quality of conduct of a review. There are other tools for those purposes. And we see this time and time again, at least when I read a systematic review, this basic misunderstanding of what this hugely influential, important paper is trying to achieve. So what can we do? So for each of these misuses, I try and make a few remarks on how we could do it better, and certainly be keen to hear any discussion people have of these ideas and others that there may be. Of course, for this one, it's probably easy. There are plenty of places that provide solid guidance for how to do a systematic review or a meta-analysis. And I've just picked a few that I happen to know better than others, including a couple I was involved in. So a bit of shameless self-citation there. So, well, moving on to the next one. The rest of them are about meta-analysis, which I imagine many people here may be more interested in. This is the I-squared statistic. This is the paper that basically promoted the I-squared statistic after it was introduced in a paper in Statistics in Medicine, which is also in the top 100 most cited papers of all time, fascinatingly, for a Stats in Medicine paper. What is it all about? Well, the I-squared statistic was conceived to measure a concept that we called inconsistency, which is the extent to which the results of the studies, as represented by their estimates and confidence intervals, are consistent, i.e. whether they line up across the studies. So that's how we conceived it. But what the statistic actually can be interpreted as measuring is the proportionate variability in the point estimates due to heterogeneity rather than chance or sampling error. And so there are two ways one might look at I-squared. The top one here, I called it iota because it's a vaguely, approximately parametric interpretation, though it's not a strictly a well-defined parameter. It's you can see on the bottom, we've got the total of heterogeneity, the tau squared between study variation in true effects, and a representation of typical sampling error. And the I-squared statistic is the proportion of the total variability that is due to the tau squared bit, the heterogeneity bit. And of course, the way we initially introduced it was through the Desmonian and led approach to random effects meta-analysis. Sorry, no, that's not true. We through the Cochrane Q statistic, which of course turns into the top one if we use the Desmonian and led estimate of tour squared. Then these are two equivalent, but they're not otherwise. So I've got a visual that tries to explain what we had in our mind when we developed the I-squared statistic. So we look at a forest plot here. Our idea was that if we look at this plot, we have an impression of the extent to which those studies agree with each other, which is completely conveyed by looking only at the estimates and the confidence intervals. So I'm essentially looking at something related to the degree to which they overlap with each other, those intervals. And the idea is that we could compare the consistency of this set of results with the consistency of another set of results, even if we've got a different number of studies and importantly, a completely different measurement scale. These are now a continuous outcome. The first one was a binary outcome in a different topic area altogether. The I-square was intended to portray the instinctive differences we see between these two forest plots. Yet it's not used in the way that we intended it. And so I thought I'd again look at the most recent paper citing that I-squared paper. And it turns out to be one from Monday this week, magnitude in terms of stunting in young children in Ethiopia. And what do we find? Well, they've used the Q statistic and I-squared and a p-value, okay, to check for heterogeneity. But they've classified heterogeneity according to whether it was low, moderate, or high, using this thresholds. I know I'm slightly to blame for people doing this, though it's not what we said should be done. So the idea is that they are thinking about I-squared as a measure of how much heterogeneity there is, which is not a measure of the amount of heterogeneity there is across studies. And this very wide misunderstanding of I-squared gets some people into very difficult and inappropriate places. If we look at it again, just to make sure we understand why it's not a measure of heterogeneity, well, clearly it's not if we look at the kind of parametric type definition, because heterogeneity, as statisticians tend to think of it, is variability in the true effects across the studies. And that is what we measure by tour squared. And this sigma tilde squared is essentially a measure of study size, which cannot be a descriptor of variability, if it depends on how many people chose to include in their research studies. So I-squared, the point, of course, is that it's critically dependent on how large the studies. For the same amount of heterogeneity, if you've got lots of large studies, they will be more inconsistent because they will have narrow confidence intervals that will then overlap much less. Of course, the solution to this one, again, is straightforward. We have a very direct measure of how much heterogeneity there is, and it is this between study standard deviation tool. Of course, it can be a difficult one to interpret. We're doing a meta-analysis on log odds ratios. Log odds ratios are difficult enough to interpret. Standard deviations of log odds ratios are pretty much impossible to make much sense of for anyone other than the most ardent statisticians. So, and I'll talk a bit about how we might re-express TOR a little bit later. My third area is random effects meta-analysis. Now, this paper is obviously a landmark paper describing what became a hugely popular specific method for random effects meta-analysis. But the most important thing about this paper is that it really was the first to lay out the idea of a random effects meta-analysis in an accessible way. And I suspect we all know, but if I just talk through what a random effects model is doing. So we've got a set of studies here. These ones we saw before, they're actually 12 crossover trials of opioids for the treatment of breathlessness and advanced cancer. And the idea is that, well, let's say they're not estimating the same standardized mean difference. There's clearly those confidence intervals are failing to overlap to such a large extent. It's very unlikely that Nutri and Kleiner, for example, estimating the same thing. So we allow there to be a difference of effect size underlying each study. Now, we don't know where they are, but we might depict them hypothetically as dashed lines in a plot like that. That assumption itself doesn't get us very far. So in the random effects analysis, we impose an assumption on those two effects that they are normally distributed across studies. And what people tend to pull out of an analysis under a random effects model is an estimate of the center of that distribution. So what we tend to find on the bottom of a forest plot is a diamond that is an estimate of the mean of that assumed distribution. Now, this is an approach with many problems. There are technical problems with the particular methods that Desmond and Laird described, which are very simple moment-based methods, but people have worked on refinements that largely overcome those technical problems, like the Hutton connection and the use of a restricted maximum likelihood rather than a moment-based estimator for the tau squared parameter. There are some really important practical problems which are largely unsurmountable unless you're really Bayesian about it, such as really estimating the fact that estimating that the width of that distribution, the standard deviation of that distribution, which is necessary to get the inference on the mean, is very difficult when we've only got very few studies. And in health and medicine, we frequently have very few studies in a meta-analysis. But the problem I really want to tackle is what I think is a bigger conceptual problem about how people are interpreting a random effects model. And I thought, well, let's find an example of that. So here's the most recent citation of the Desmond and Laird paper, again from earlier this week. It's from Animal Health, Porcine Bovine Bone Xenografts. No, they're the bone. I haven't really read it. I just picked it out. Like the xenografts, probably for treating humans, actually. So they have observed their heterogeneity and done a random effects model. So they've found no significant difference between the two treatment options here. This actually does exemplify the problem, but not very well. So let me skip to another problem. Let me go back to this one that I used slightly earlier, the one of looking at stunting in Ethiopia. This is a beautiful example of what I think is the problem with people, how they interpret random effects models. So they recognize here in this extract that there was variation in the prevalences of stunting across studies. And they do an overall meta-analysis with the random effects model. And they produced the overall pooled meta-analysis, showed that the incidence of F stunting was 30%. Now, the incidence of F stunting is clearly portraying to the reader that there is an incidence of F stunting. And yet nowhere in here is there any indication that this is from a model that is specifically saying the prevalences vary across studies. And if you want to see how they vary across studies, here's the forest plot on which that was based. And the idea that these studies with hugely variable prevalences are well represented by saying the incidence of F stunting was 40.3% is, of course, pretty absurd. So the problem is that random effects meta-analyses aim to learn about distributions, not about single effects. And people really don't recognize this, or at least they don't convey it in what they write. And of course, I mean, Desmond and Laird were really clear about this. They opened the discussion. We've used a simple random effects model for combining evidence to characterize the distribution of treatment effects in a series of studies. And this is just lost in common practice. Of course, the solution to this one is it's not quite perhaps as straightforward as I think the earlier ones were. The debate between fixed effect models and random effects models is not over. There are still strong beliefs on either side. not necessarily about what people now call the common effect or the equal effects model versus a random effects model. I think that's quite clear. But there's an interpretation of the fixed effects meta-analysis results that doesn't require assumption of a single effect. And so it's always a viable option to do a fixed effects model. I probably should have put an S on that. But if we do a random effects model, I think the solution is in a way straightforward. We just need to make sure that we present or portray that this is an overall average or a mean of a distribution. And so we should somehow portray that distribution. We can write some qualifying remarks in the text, or we could do some statistics. And for me, in many circumstances, but not all, a very useful way to portray that distribution is to compute a simple prediction interval, which we've written about in various papers, which is an interval in which we would expect 95% of true effects in future similar or exchangeable studies to lie. And we can compute that and illustrate it by, for example, extending a line beyond the diamond to represent the distribution of effects, not just the uncertainty we have about where the mean is. Okay, as my last gripe, as it were, the use of the EGA test or any test or statistics based around funnel plot asymmetry. I mean, funnel plots are great things if interpreted appropriately. I mean, what is it? It's just a plot of the sides of the effect against some measure of precision, maybe as simple as the study size, a sample size, but more usually it would be a statistical measure of precision like a standard error or a variance. And this plot is taken from EGA's original paper to illustrate how it works in practice. The idea is that if we apply this to randomized trial, we would expect a funnel plot to be symmetrical, because the large trials, which we see here plotted towards the top, the high precision trials, should be near the truth. And as we make the trials smaller and smaller, we come down the plot, we expect them to be scattered, but they should be centered around the same truth if they are all estimating approximately the same thing. That's the theory. Whereas in the two lower examples, it's clear that the smaller studies are distinctly to one side of the result from the large trial, which raises questions. There are problems there. The problem I'm talking about is that people then, well, let's have a look as an example of what people do. This is the most recent citation of the EGA paper from SciLit. It's looking at alcohol use in young people. And they use forest plots for visual interpretation, find funnel plot asymmetry in EGA's test used to detect potential publication bias. Is that a valid thing to do? Well, I mean, they've written the word potential in there, so I'm not too critical. But then you look at the results and they say, EGA's test showed no evidence of publication bias. Now, the problem here is that people almost universally in the applied systematic reviews field equate funnel plot asymmetry with publication bias in a way that I think is just not appropriate. Funnel plot asymmetry can arise for a number of reasons. It can arise because of particular types of publication bias or other reporting biases like selective outcome non-reporting. But it could just as viably arise due to issues of study quality. Very often, particularly when we move away from randomized trials, it's due to just genuine heterogeneity of particular sorts. Of course, when we're using EGA's test, there is a technical problem that can induce some artificial correlation, but I think that's fairly small compared with the more substantive issues. Of course, chance, but the statistics should deal with that. So let me just show you a couple of the ways in which funnel plot asymmetry will be induced by things that are nothing to do with reporting bias or publication bias. Suppose our smaller studies are done less well than the bigger studies. That's a perfectly reasonable situation among randomized trials, or indeed any study. design. And this is depicting the idea that maybe the smaller studies are, and this is an exaggerated example, they're just shifted because they all suffer from the same sort of bias that is present coincidentally in studies that happen to be small. Well, how about this one? Here's a funnel plot that certainly looks asymmetrical, I would say. And so people may, would frequently conclude that there is publication bias. But no, there's something else going on here. If I actually label the studies according to the type of study, this is again a hypothetical example, but you can see how it would bear out in the real world. Basically, what I've got superimposed, there are 3 sets of studies that are different and probably might not have been reasonable to put them together into one meta-analysis. And if we look at each one in turn, there's a perfectly reasonable funnel plot asymmetry within each subpopulation, that when we put them all together, it has the appearance of asymmetry, which is asymmetry, and we would just be wrong to conclude that it's because of publication bias. So what's the solution to this one? I think the solution to this one is just to move, if you're interested in publication bias, don't start with statistics. Start with using your head and thinking through the likelihood of non-reporting. We can look at outcome non-reporting, of course, by looking at the papers and looking at whether they may have measured outcomes or done analyses that they suppressed from the report. The publication bias is a lot more challenging, but people don't frequently enough, in my opinion, think about the situations in which people may be able to or want to suppress findings. So, for example, in an era where randomized trials are all pre-registered, it would be very unlikely that in some areas, not all, that a trial will be done without you knowing anything about it. So one can use the trials registries to trace the trials and learn about studies that have been suppressed, rather than using statistical methods. And of course, we need to take into account the nature of the studies. The funnel plot theory works well for randomized trials, but I don't think it necessarily works for other areas. I see no reason why a meta-analysis of prevalence should have issues of why publication bias should induce funnel plot asymmetry. And no one's convinced me why that should be a general phenomenon. So people don't think hard enough. Of course, I've worked on a framework for thinking about publication bias and reporting bias through our ROB-ME tool, risk of bias due to missing evidence, that tries to put these ideas into a framework that people might want to use if they want to think about publication bias in a review, particularly randomized trials. And there are ways that we can look at funnel plots more carefully, as many of you will know, using contour-enhanced versions of funnel plots, where we use contours to describe levels of statistical significance. And here are some lovely examples, I think, come from Alex Sutton. There are 2 examples here. On the left-hand side, there is appearance of asymmetry. But what the contours represent are the statistical significance that each result would achieve in isolation. So the ones in the white area, these are the ones that would be non-significant. And the ones in the light gray area to the edges, here and here, these are ones with a p-value less than 0.01, so pretty significant. And the magic boundary is the one between the two middle grays. That's the p equals 0.05 boundary. And what we see here is that the studies that we've got all happen to be statistically significant. And if there is a gap here from a symmetrical funnel plot, then the missing ones are in the area largely of statistical non-significance. So this is very much compatible with the idea of publication bias, in that the significant results are available to us and the non-significant ones are not. On the other hand, in the other plot on the right-hand side, the opposite is true. If we were to take the funnel plot asymmetry theory equals publication bias as true, then we would be saying that this large study is near the truth, and there are missing studies down here. Now, these studies down here are the ones in the statistically significant area. So is it really plausible that they have been suppressed and that all the non-significant ones have been published? Well, sometimes that will be the case, for example, if this were an adverse effect, but I think it's not. And then this is a situation that just isn't really compatible with the asymmetry being due to publication bias, and it's probably due to something else. Okay, well, that's really all I wanted to say. Just a few closing remarks. I've reviewed what I think are some of the most common errors that I see in systematic reviews and meta-analyses around the areas of reporting, identifying heterogeneity, dealing with heterogeneity through a random effects model, and assessing bias, and try to offer some solutions. But this is I think the fourth or fifth time I've given this talk, and each time I've done the same thing of looking at the most recent citation. So it's not just a fluke this time. Every single time, maybe bar one or two, which were not brilliant examples, but were certainly not beautiful pieces of work, I found the method to be what I think was misunderstood or misused. Of course, because of what I've done, there are many examples that are worse than the ones I've shown you today. So I think, although I haven't done an empirical study, and I would love to do one if I had lots of time and money to see how bad the problem really is, my impression is that this is just, we're in a terrible state of the systematic review literature, as I think many of us will have recognized. Why is this? Well, maybe you could help with some discussion of this. I'm sure a lot of it is people just copying from paper to paper, do a systematic review, look at another one and do the same thing. And if that one has made these blunders, then the new people will make the same blunder. I worry that there may be some teaching, some guidance out there that is setting people off on the wrong path. It may just be that people assume methods are doing things that they aren't actually doing, but would rather that they do. So that's wishful thinking. But I think the important thing, I think, for certain people at a conference like this is to ask how, if at all, our software can help avoid making any of these mistakes, or at least reducing the number. So my final remark, I mean, I'm often, people see that I'm highly cited, and it's quite nice to get this sort of recognition, but it's also quite embarrassing at times, because it doesn't necessarily mean that people who write papers that are highly cited are having a positive influence. So I will leave it there. Thank you very much for your attention.
Thanks, Julian. Do you have time for some questions?
I do, yeah.
I'll just give it a minute for the live stream to catch up on YouTube. And if anyone wants to ask any questions on the Zoom, if you can ask them using the Q&A functionality. Okay, we've got one from the Q&A. Kate asks, first a question, what if authors whose methods papers start to accrue a lot of citations were invited, brackets, expected to write up a commentary about typical misunderstandings of their paper? What should the trigger number of citations be?
Oh, that's interesting. And then the question is whether it should be a trigger absolute number or a trigger proportion of citations, because if a paper cited 20,000 times and only in 150 of them is it misused, that's pretty good hit rate, whereas 150 out of 160 misused is pretty bad hit rate. And that's potentially, if the paper's on the rise, much more important to address the second than the first. And as any statistician, I'm never always reluctant to give any threshold, so I won't give one. But of course, this all also rests upon the idea that someone is counting and looking at misunderstandings. And unless that is in place, then I guess the question's a moot one. But thanks for it.
Okay, while we wait for more questions, I'll ask one quickly. How much of this is publishers and the peer review process to blame?
Well, I mean, in a sense, all of it is, because if these are genuinely misinterpretations and misuses, as I believe they are, then that's a failure of peer review and editing to pick them up. I suspect we've all come to the conclusion that peer review is in a desperate state because there are so many papers and not enough knowledgeable people out there doing peer reviews. So it's responsible, but it's not at all easy to see how we could fix it.
Thank you. We've got one from Samuel online. Says, thanks for the nice talk. Do you think meta-analysis / systematic review software should provide some kind of correct interpretation of I-squared, Eggers test, etc., to avoid misuse and understanding?
I think it would be very helpful. I would stop short of saying it should. I wouldn't want to dictate what output produces, but I know there are some programs that do bits of writing of results for you, and I think for a lot of users that will be incredibly useful to get them on the right track. Yeah, of course there are some people who know what they're doing would find it really frustrating to have wordy explanations when they're just looking for the numbers and they know exactly what to do with them. So, I suppose ideally a default to present explanations with the option to turn it off. The dangers, of course, there are with that is that people will just turn it off and be none the wiser.
Thank you. We've got one from Matthias. I hope I'm saying that correctly. I have started to like the fixed effects model. What is your take? Not to start a big discussion.
I have opened up a bit more recently. I mean, I wrote this paper with Ken Rice and Tom Lunley about interpreting fixed effects meta-analyses. And it became clear, well, some while ago that there is an important distinction between the fixed effect model and the fixed effects model, where the studies are all equal effects or they're different but not related to a distribution. And under that second model there is an interpretation of the fixed effects analysis, and I think that is entirely reasonable. The only problem, of course, is that it completely ignores heterogeneity. So one would have to supplement it with something around heterogeneity to provide a good interpretation of it. So for very similar trials, I think for meta-analysis of drugs at similar doses and schedules and so on, similar lengths of follow-up, I think the fixed effect is entirely justified, even if there's statistical heterogeneity. But I think once you start moving towards understanding different interventions or different interstudy differences rather than interpatient differences, then you might start thinking about random effects rather than fixed effects.
Thank you. We have one from Alicia. Many people conducting meta-analysis don't have a formal training or courses, and that's probably where misunderstandings can come up. I'm wondering if you have any suggestions on how to navigate training or resources without the training.
I think that's a really, really important problem, that people are just doing these. They're told to do them. PhDs or clinical research without formal training. And all they've got to go on is copying all the various rather long-winded documents like handbooks and so on. Do I have any useful comments? No. If anyone else does, I'd love to hear it. But I mean, maybe there are more resources that could be set up sending really simple messages in ways that bring people in, that really attract people. There has to be some sort of carrot to bring people to the right places. And I don't know what that could be.
Thank you. Just on that point, we do have a keynote tomorrow about learning to synthesize by Mark. And we have a couple of points from Matt on YouTube. On the misinterpretation of reporting guidelines, to what extent do you agree that whilst not intended as guidelines for conducting a review, they have come to serve this role in a small way? A lot of the time I see reviews saying they followed PRISMA when they did not. So at least if the paper follows them, it gives me some confidence that they are taking systematic review process seriously. And finally, particularly important for non-medical fields, I feel where all the steps of a review are rarely followed.
Yeah, okay, that's a very fair point. I mean, it's way better that they read PRISMA and take it on board than they look at nothing. I think a way of interpreting what you're saying. Yes, so that is very true, particularly in areas where the systematic review toolkit is not quite so well as established as it is in health and medicine. So absolutely, that is true. And of course, I mean, there's a huge amount of really useful stuff about conduct in the elaborations of PRISMA. And so it is a very useful document to read to learn about systematic reviews. Yes, I absolutely take that point. It's just a shame that there are actually better ones that would tell them how to do it more clearly than the indirect way that it does in PRISMA.
Thank you. I believe that's all the questions, unless anyone has any last minute questions. I'll just give the live feed time to catch up. Matt says, thanks. Okay, I will conclude that session. Thank you very much, and thank you for everyone who is watching live or will watch later on catch up. Thank you.
Thanks. Bye-bye.